Now, seamounts are individual volcano mountains, or volcanic mountains, I mean. These are submarine mountains that are not part of a mid-ocean ridge. So that, those long mid-ocean ridges are basically a whole mountain chain, but these seamounts aren't connected to a mid-ocean ridge. Something else created them. There was a different source of magma that burst through and solidified, creating these islands or submarine mountains. At one end of a chain of these, because they're always in chains, is very often currently an active volcano. An example is the Hawaiian Islands. We've got a series of islands that stick up out of the water, and if you look at a bathymetric map, beyond the islands are a bunch of submarine mountains. They're submerged, but they're still mountains. And they're in a big, long line. The southernmost one is the island Hawaii, and it's got active volcanoes. This happens when you have a hot spot in the mantle, this super hot area that is providing magma that is rising and bursting through the crust. It creates a chain because that crust is moving constantly. That's plate tectonics. Our crust is moving. It's broken into plates, and each plate is doing its own thing, moving along. And so if that plate moves along over this source of magma, the magma can punch through, create a nice little mountain, but then the plate moves along, and now it can't get through in that mountain anymore, so it punches through and makes a new mountain. Imagine if you've got, say, like a paintball gun, and you're going to hold your paintball gun perfectly steady, and somebody's going to take a piece of plywood and move it along in front of your paintball gun, and every few moments you pull the trigger. You're going to get a whole row of paint splatters because that plate, that plywood, is moving in front of your hotspot or moving in front of your paintball gun. The last one is the newest or youngest one. It's the one that's in front of that paintball gun, the one that's above the hotspot right now. The one furthest away is the oldest one. It was the first, and it's the oldest. The same way with the Hawaiian Islands. A guyout is a flat-top seamount. It was one of these volcanoes, and the surface or the peak of it has completely eroded away, and the waves knocked it flat. Eventually, it can sink deeper. It doesn't erode deeper. It won't ever erode below the surface. It can erode to the surface, but because of temperature changes and buoyancy and possibly sea level changes, it can end up submerged. And so you have the flat top, but underwater. And it's called a guyout. Before it gets submerged, usually a coral reef is going to grow around it and on it. But if it gets too deep, the coral will die, and all that's left are the skeletons of the coral. Because the coral has to be close enough to the surface for the right temperature and light and food source conditions. Now, moving on to continental crust. The continental crust is 4 times, roughly, as thick as the ocean crust. Instead of being 6 to 10 kilometers thick, we're looking at 35 to 40 kilometers thick average. There are places where it's thinner and places where it's thicker, but this is the average. It does have variable thickness and height because of mountains and rifts. Mountains are the thicker places and rifts are the thinner places. There are differences in composition, the elements present, the minerals present. The continental crust is silicic to intermediate, so much more silica, although as you go deeper and deeper, you become a bit more basaltic, so less silicic as you get super deep. But that's quite different than the oceanic crust, which is basically pure basalt, except for the sediment that sits on top of it. So, if we look at the crust, we've got this silicic to intermediate upper crust, and this extends down 17, 18 kilometers to where it starts becoming more mafic, the mafic lower crust, and then we hit the moho. The moho is the bottom of the crust. There's no crust below the moho. This little weird line on the right here is showing the strength of the crust. It starts out with a nice straight line, getting stronger as you go deeper because you're compressing the rock. It's like, it refers to it as the frictional sliding law, and it makes sense. You have rock sitting on top of another rock, and you can slide it. You have somebody stand on it to add more weight, and it's a lot harder to slide it. You get a couple of people to stand on it, and it's really hard to slide it. There's more and more friction. But that only applies until you get to a certain depth. At a certain depth, because the temperature is also rising as you get deeper, it starts to act plastically, and you get deformation, and it actually gets weaker. It's no longer hard, rigid rock. It's hard, plasticky rock. And as you get deeper and deeper, it gets hotter and hotter until at the base of the silicic and intermediate part of the crust, there's an abrupt change as you get more mafic. And the strength jumps up. Because that basaltic rock, that more mafic rock, is stronger at that given temperature. But you keep going deeper, it keeps getting hotter, and even that starts behaving all soft and plasticky. Now, mind you, this isn't as soft as plastic that we can do stuff with. We don't have, silly putty and Play-Doh down in the lower crust and mantle. That's not what I mean by plastic. It's still rock. It moves very slowly, but it does move. And then we hit the moho, and there's another composition change. And instead of being just kind of mafic-y and basaltic mixed with our intermediate silicic stuff, it jumps to olivine. Very mafic. And there's a strength jump, and then it starts doing that curve again. So you can see that's how we know about these changes, is because of the strength, which we can also see in other ways like the seismic. So what are the categories of crust? How are we going to put it into nice categories and bins? We like giving things names and saying, oh, it's this and oh, it's that, right? Scientists love to do this. So how are we going to categorize the crust? Well, we could use this categorization. Unfortunately, it's not all that appropriate, even though it kind of looks delicious and I think I'm getting hungry. Well, except that bottom one. That bottom one, not so yummy. So this is not how we categorize the Earth's crust. What we do use are terms like this. We have Precambrian shield, we have continental platforms, we have cratons. The Precambrian shield is always plutonic and metamorphic rock that's been around since before the Cambrian, thus the name Precambrian. An important thing is that this is the area where this is the current bedrock, the top rock. The only stuff covering it is like unconsolidated sediment and trees and buildings and people and stuff. But it's the first rock you hit if you dig down into the ground. Other places you hit other kinds of rock first, such as in the continental platform. This is where the Precambrian rock, which is still there, then has other rock on top of it, as late Precambrian, specifically Neoproterozoic, and or Phanerozoic sediments. So we have sandstone and limestone and shale and all these different sedimentary rocks on top of that Precambrian rock. The weird thing is that you can have Precambrian sedimentary rock on top of Precambrian crystalline rock and still have it be a continental platform and not be a Precambrian shield. But it's only that very end, the Neoproterozoic. Then we can talk about cratons. This is old, relatively stable continental crust. Basically, it's not a rift zone, it's not a subduction zone, it's kind of boring, tectonically speaking, but it's a good, safe place to build tall buildings, for example, because you're not worrying about earthquakes. We can look at orogenic belts, especially younger orogenic belts. By this we mean anything from the Neoproterozoic to current. And they can be active or inactive. Something like the Appalachian Mountains, they're inactive. They're technically shrinking right now because there's erosion going on, making them shorter and shorter every year. Very slowly, but it's happening. And then we have things like the Himalayan mountains and the Alps and the Andes mountains. The Andes are definitely growing. That's an active orogenic belt. Rifts, on the other hand, are places where the lithosphere has been stretched, thinned, or even ripped apart. And again, these can be active or inactive. So you can have basically a rift scar where it started to rift but things changed and it no longer is ripping apart there, but it is thinned, so you have an inactive rift. Or you can have places where it's actively still stretching and thinning and ripping, and give it another million years and you'll have beachfront property because it'll rift apart and the ocean will flow in. We have passive margins. These are places where it created beachfront property. Rifts broke apart and are now separated by an ocean basin, and so that edge of the continent is a passive margin. Oh, and I left off one. Active margin, which is a subduction zone. So a couple of things here. We've got a rift zone, the East African Rift. We've got part here, part there, and part here. This is a rift zone that's active. We have the Basin and Range in the United States. This is a rift zone that most of it is becoming inactive, but it's still pretty young, and therefore, there's stuff going on. There are still earthquakes, there's still high heat flow and so forth because of the rifting. We can look and we can see these three different colors, the gray, the dotted, and the white, covering the continents, where the gray are the shields. The polka dots are the platforms, and then the white is orogenic crust, built by mountain building events. So we can see the Appalachians, an inactive. We can see the Andes, an active orogenic crust. We can see the big Canadian shield. It's a term you hear a lot in North America. And then we can see the continental interior platform, which is where like Grand Forks is. And we can see shields and platforms and orogenic crust all across the world. Zooming in a bit to North America, you can see the shield and the platform and the orogenic crust, and then some coastal plains that are basically created by eroding those mountains. We can also see things like the Colorado Plateau, not one of the key provinces, but still a very large feature. So the moho. I've heard this term before, hopefully before today, but also I mentioned it earlier today as the bottom of the crust. So what is it? Well, the full name is the Mohorovičić discontinuity, discovered by Andrea Mohorovičić. And that's not a typo, it does end with a double IC like that. Which is why we generally call it the moho. A lot easier to say than Mohorovičić. It is a seismic disconformity or discontinuity. So an abrupt change in speed of the seismic waves traveling through the Earth. It marks the base of the crust. In the ocean, it's about 5 to 10 kilometers below the ocean floor. Again, you remember the ocean floor or the ocean crust, 6 to 10 kilometers thick, 5 to 10 kilometers thick, something like that. So the base of that is where the moho is, because the moho marks the base of the crust. In the continents, it can be anywhere between 20 and 90 kilometers below the surface. Now we said the average for continental crust is like 35 to 40. But then we have rift zones which are thinner. We have mountain zones which are thicker. And that's why we have this 20 to 90 kilometers down for the moho. Above the moho, seismic velocity, the speed that those vibrations travel through the rock, is around 6 kilometers a second. Below it, it jumps up to 8 kilometers a second. So, gaining 2 kilometers a second when you were at 6 previously, that's like a 33% increase in speed just for crossing that line. It's a big deal. It's a very distinct change. In the oceans, it's a sharp line. It is an abrupt, distinct change. Very clear what's going on. Under the continents, in some places, it's a distinct line. In other places, it's a more gradual transition, where that transition can take place over 2 to 6 kilometers. In those cases, it's because the rock doesn't change abruptly. It's kind of a gradational change in composition. Again, because plate tectonics are going on, and so things get mixed up sometimes.